Hello, my name is John. This is my course project for Duke's Machine Learning for Product Managers course. We're going to cover an analysis of a combined cycle power plant where we are looking to better understand the impact on a model if we remove one of the input features. We'll start with the context and data, cover the modeling approach, talk about evaluating the models before, after the change, and finally wrap up with our findings and recommendation. We're using a hypothetical scenario where questions have come up related to the cost of continuing to take the temperature reading. Due to changes in technology and increasing operational costs, the cost of collecting temperature readings in the same manner we have has gone up by 5%. So let's start with the data. Using a data set of 9,568 sets of readings, with each set representing 4 individual readings for a total of almost 48,000 readings, we can see the ranges across the different readings for this data and their subsequent impact on electrical energy output, which is our target variable. Given this is one of our first set of models, we will have different multiple input features in our model, and we prefer to minimize costs on building more extensive models. We'll start simple with a multiple linear regression analysis. We will separate the data, reserving 20% of it for validation purposes. This data will be removed from the middle of the data set. Given the simplicity in communicating the results as it relates to the cost of continuing to measure temperature, as well as the focus on controlling investments and building complex models, we will use a simple multiple R as a proxy for accuracy and R squared to understand the variance in the target due to the input variables. Let's go in and take a look at our models. So here are our summary metrics, but let's go look at the details. Our first model, the training data, shows a multiple R representing a high level of accuracy when predicting future targets. In addition, the R squared gives a high level of confidence that variances in the target variables are attributable to changes in the input features. You can see that here. The Model 1 validation data set further validates the findings in our training data. Now, when we look at our second model, which removes the costly temperature reading consistent with the scenario explained earlier, we see a material effect in our multiple R and R squared. Our multiple R drops almost 7%, while R squared falls 13%. We see something similar in the validation data, with multiple R and R squared falling 7.5% and 14.7% respectively. So, as we've shown, including temperature in the model has a material impact on the model's ability to accurately predict the electrical output. Removing it drives a 7% plus decrease in the accuracy of future predictions in both the training and validation sets. Including temperature in the model increases the correlation of the input variables to the electrical output. Removing it will drive our R squared down 13% plus and cause the model to be underfit. So as a next step, the recommendation would be to evaluate the cost of continuing to measure temperature, which would include absorbing a 5% increase against the potential impact of predicting the electrical output with this decreased level of confidence. Thank you.